our products end up a little bit different. We end up keeping a ketone, and we end up with a beta ketoester at the end of a Claisen condensation, because we have a leaving group, right? Unlike aldehydes and ketones, where we don't have a leaving group, so when we do aldol reactions, we end up with an alcohol there, and then we can do dehydration. Dieckmann condensation is literally a Claisen condensation, but it's intramolecular. It all happens within the same molecule. So you've got an ester at either end. Did I say ether before? Or did I say ester? Claisen is like an aldol, but it's an ester. Did I say ester? Okay, good. Just making sure, because I could have sworn. All right, so we've got an ester at either end. There it is. And basically, we're going to do just a normal Claisen condensation. The only time a Dieckmann condensation is going to work, so the only time intramolecular Claisen condensation is going to happen is when you get a 5 or 6 membered ring. So anything else, nature's not having it, but a 5 or 6 membered ring, absolutely. And don't ask me why, but it gets a whole new name. So the mechanism's identical to that of Claisen because, well, it totally is a Claisen and it doesn't need its own name. Arguably, it doesn't deserve its own name. So we will move on. Crossed Claisen condensation. Crossed Claisen, much like a crossed aldol, is when we're going to have 2 different starting materials. So Claisen esters, 2 different esters. If you just have 2 different esters and they both have 2 alpha hydrogens, you're going to get 4 beta ketones at the end, and none of this is going to be useful, right? Because, God, I mean, they're all going to be so dang similar in polarity and molecular weight and, like, everything that we use to separate compounds, right? Like, they'll be slightly different, but not different enough to, like, usefully separate those guys, not easily. God, I can't even imagine that column. So basically, cross Claisen is not going to be synthetically useful unless you've got one of them that doesn't have any alpha hydrogens, so it can only be the anion acceptor. So, same as aldol reactions, but in this case, we also make this happen the way that we want it to happen by using an excess of the ester with no alpha hydrogens. So, this guy. No alpha hydrogens, use a bunch of that, because there's no way we can get a Claisen condensation between this and itself, right? So we put a ton of this in there, and then this, we could get a Claisen condensation between this and this, or between this and itself. So we just make sure there's so much of this around that the likelihood of one of these guys, once it becomes alpha deprotonated, the likelihood that it runs into one of itself instead of one of these is pretty low, and then we get mostly what we want in the end. Yeah? Let's see. So yeah, we use that in excess, and, you know. Let's see. Retrosynthetic analysis for Claisen and Dieckmann. So we know that we end up with a beta ketoester, and if we already know it's a Dieckmann condensation, that's nice because we know that we have 1 starting material, right? If it's a Claisen, then we're going to have to split it, and we're either going to get 2 of the same thing or 2 different things, right? But for Dieckmann, we're going to basically slice it. Let me make sure that I'm doing. Why are they? there's so many R's. Okay. We're gonna have the, yeah, we can do, let's see. R1, R2, R3, R4. Oh, they put it down here, didn't they? Fine, I guess we can do that. That's alright if you want to make your beta, well, sure. But, so, where we break this is gonna be one of these bonds between our carbonyls, right? But which one is it? How do we know? Who's got a guess? So one of these guys, one of our esters is going to be, well, that looks like a face, but whatever. It's going to have a negative charge right here, right? And so it's going to, whatever else is attached here, it's going to attack from here. So one of these guys needs to stay connected to its carbonyl. The other one is going to get attacked, right? So the one that gets attacked in an aldol reaction forms an alcohol. But in this case, why doesn't it form an alcohol? Or why do we end up reforming our ketone? Because we've got a leaving group, right? So the one that gets to keep the one who gets to keep his alpha carbon, the one whose bond we don't break closer to him, is the one that still has its leaving group. Because we didn't mess with this carbonyl carbon, right? We didn't attack this carbonyl carbon. This guy is just helping stabilize this nice negative charge so that this guy can be an effective nucleophile. So we're gonna do this. And then, right, yes. And then we're gonna have R1, O. I'm gonna go with probably R4 because it's probably gonna have the same type of ester that you start with, just for convenience's sake, so that you don't end up accidentally transisterifying things, honestly. So that's our starting material here, and our starting material here is gonna be R2, R3, O4, that, right? In this case, we've got, yeah, it's kind of a mess, but, and it also kind of looks like we probably have a crossed claisen here. I mean, it looks like a crossed claisen because I just didn't specify that one. So in order for this to have happened, this one needs to be like that or something, right? No alpha protons. But that's kind of how you're gonna break this up. For a Dieckmann condensation, you do the exact same thing, except now I have to draw a 5-membered ring that I don't like to do. Okay, so we're still going to break it close to what is now our ketone, right? Not close to what is still an ester. So we're going to break it here, which is perfect because we're breaking apart the ring, and that's the whole thing with Dieckmann condensations. So we're going to break this right here, and we're going to end up with, and let's just start counting. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. What's that here? So 6 is the next carbonyl carbon, and then we have probably a methyl ester because that one was a methyl ester. And then if we had any sort of substituents on any of these, then good thing we numbered them all because now we know, oh, 3 seems to have a methyl group and 5 seems to have a methyl group. And that was not supposed to look like a loop, but whatever. Yes? Cool. So, backwards reactions. Let's see. Hydrolysis and decarboxylation of beta ketoesters. So, we have a beta keto ester. We've heard of beta keto somethings before, right? We've done something with that before. We had beta keto carboxylic acids, right? And when we heat those guys, like mild heat, they just sort of CO2 pieces out, and that hydrogen that was on the COO group, COOH group, just sort of replaces where that COOH group was. So it's just CO2 gas, hydrogen comes in, there we go. So this gives us something that kind of looks similar to that, but it's not quite, right? We can't just heat this and then there's a whole R group, right? How do we get rid of that R group? You can use saponification followed by acidification. All right, do you have to do it that way? Can you just do? Okay. They do saponification followed by acidification because Fischer esterification is only acid catalyzed, so you can do hydrolysis of an ester in acid, but like that's going to be equilibrium, right? Because hydrolysis of an ester in acid is the exact opposite of Fischer esterification, which can only be catalyzed by acid. So in this case, they're going, you know what, let's just skip all of that equilibrium nonsense. Let's just get exactly what we want and all of what we want. So they do saponification, which is hydrolysis in a base, which doesn't go backwards, and and then they're gonna get the anion here, and then they go, all right, cool, let's just work that up with a tiny bit of water, or some water and a tiny bit of acid. Notice the hydrolysis is being heated up, so like once we cool it down, we add some acid. To work that up, we get this, and then you do mild heat, and this is a beta, right? Because carbonyl, alpha, beta. Yes? Beta keto, not a beta keto ester anymore, a beta keto acid now. And so CO2 right there pieces out, and now we've got just a nice little ketone. If we did a Claisen condensation, not a crossed Claisen condensation, we end up with a symmetrical ketone, because we started with the exact same thing, CH2R connected to a carbonyl, and that guy gets to keep his carbonyl because this is the one that's going to get attacked, so it's going to get, it's just going to keep the side leaving group, right? There's no bond happening over on this side. That leaving group's gonna happen. This guy, this is the alpha carbon that's going to be doing some stuff, so this guy attacks that, and we get a bond between those two carbons. Yep. And then once this stuff pieces out, then we just have, well, a CH2R, which is the same over here. So we get, it's symmetrical. Yeah. Obviously that's only if it's a normal Claisen condensation, not a cross Claisen condensation, but we don't do a whole lot of cross Claisen because aldol is easier. Crossed aldol is easier. Let's see. So, carbonyl condensations, all of these guys, they're most widely used reactions in the biological world. I mean, I don't know if they're talking, I assume they're talking about in nature, like, not in the world of biology and biochemical research groups, because it would just be useless to make a claim like that about most commonly used reactions in research groups when, like, I don't know, I mean, that would change year by year, like, very quickly. Yes?
I think it's just for, like, photosynthesis.
Yeah.
That's what that is.
Oh, they're saying the most widely used because it's photosynthesis,
Yeah.
and photosynthesis happens the most often.
Yeah.
Oh, they're not saying it's a lot of different ones. They're just saying
Yeah.
photosynthesis happens the most out of all things.
Yeah, it's because it
Oh, okay, thank you. I was just like, why are they, okay, yeah. Photosynthesis, there we go. Photosynthesis happens a lot. And it's a carbonyl condensation, I guess. Really? Yeah. Good, cool. Yes, you can learn one kind of chemistry and completely ignore the other ones, eventually. You have to get through the other ones, but like, once you limp through the other classes, you just decide you're done with those. Pick one and stick with that. So, let's talk about enamines. These are formed by the reaction of a secondary amine with an aldehyde or a ketone. Because if we took a primary amine and reacted it with an aldehyde or a ketone, we would get an imine, right? This guy plus N is going to give us 1, 2, 3. That, right? So that's not what we're talking about. I mean, then I guess you could try and deprotonate one of these, but in this case, if we just have two substituents on our amine in the first place, then we don't really have the option to form an imine, right? And so we definitely can only form an enamine. Enamine? So the English language makes me want to pronounce that enamine. And enol, being based on alcohol and alkene, and this being based on alkene and amine, makes me think that this is probably enamine, but I feel like that just sounds dumb, and I don't like it. So there's a solid, like, 65, maybe 75% chance that I'm pronouncing this wrong when I say enamine, but enamine sounds dumb to me, so whatever. Right? I mean, I don't know. Chemistry is weird like that. Because like there are so many things, like you can come up with so many names that already exist just because of IUPAC. Like, it definitely has to exist, right? But how do you pronounce some of those once you end up putting some of the wild combinations together? Someone may have never written that name out or tried to say that name out loud ever before, so like, what are the rules? I don't know, sometimes, I don't know. I've decided it's enamine. So, we are gonna use, usually we use those guys, pyrrolidine and morpholine, so I like morpholine better. Can you guess why? Because I'm a master at hexanes, and not so much pentanes, cyclopentanes. So, we're going to use these guys, and basically, when we put that with a carbonyl, aldehyde or ketone specifically, we end up with that. because we're going to, I mean, basically we can just, here, let's see. I think I actually do the, yeah, I'm doing the whole mechanism for you, so. Oh no, we've done this before, right? Have we done? Yeah, we've done this before because what happens is we kick this off, right, and we form that, and then we just end up going, hey, one of these guys is acidic, so we have base take that, electrons go up, and we get a much happier nitrogen. Yes? So we do sort of make an imine in the process, but like, yeah, obviously it doesn't stay there. So these are pretty nice because the beta carbon is a nucleophile by virtue of the conjugation of the CC bond. Is that because this guy is the alpha carbon now instead of, I don't like what they're saying. I think that they count this differently now. So with carbonyl carbons, or with carbonyls, this is the carbonyl carbon, so we count from here and we go alpha, beta, etc. From here, well, it's not an imine, right? So it's just a single bond to the nitrogen. So I think that what they're doing is they still mean the same carbon that we've been calling alpha while it was a carbonyl carbon, but now it's beta because from the nitrogen we count alpha, beta. That's annoying, and that's not something that I'm gonna try and trick you on because that's dumb. So just keep track of where the carbons are and which ones we're talking about, and it's supposed to be fine. So they do a bunch of stuff that enols and enolates do. We can do alkylation of enenes. So